So hello everyone. Today I'd like to discuss about the basics of speech processing. Now, what is speech? Now, speech is basically a type of sound which include different phonetic features or say phonetic content based on which we can express our feelings, our views to anyone. Now, while we talk to someone, when we express our feelings to someone, so we must have someone to understand what we are saying. So in any discussion we have a talker and a listener. Now, talker is basically the person who is generating the speech, and listener is basically the person who is recognizing the content of the speech. Now, when we generate speech, when we talk, so there are certain things through which our whole speech processing system goes through. So initially comes the this message formulation. So message formulation is basically means what we are trying to say to the listener. Then comes what language we are trying to say. Then comes the emotion of the speech and etc etc. Once all this formulation get formulated, thereafter comes the our vocal or sound production system. This vocal tract, this other parts of the vocal tract, say nasal cavity, oral cavity, etc etc. Now, once the speech is generated by our sound production system, now this comes in terms of acoustic wave. That is the normal sound. Now this sound that contains the different phonetic content or the speech content goes to the human hearing system of the listener, and the listener try to understand or try to recognize each of the content. Now let us today and try to understand how this speech production system, that is the generation system, works rather than the recognition. Now we have the most important part of this speech processing system is our lung. So as you can see over here, it is a schematic overview of the human speech processing system. So you can see over here is a large volume of air, and the piston is trying to push all the air, and when the air comes out from this specific part, so there are two ways it can goes through, similar to that of human speech production system. So your lungs is the responsible for the airflow, and when the airflow comes out the vocal tract, it goes through this oral cavity or mouth cavity and nasal cavity, and this whole system is called our vocal tract, and it is the main part of the human speech production system that makes different phonemes, different types of sounds. Now the whole thing can be understood in that way. Say for example, in terms of digital speech processing, say for example, xt is a signal, and this is say glottal impulse. Now what is a glottal impulse? That is the basic airflow that is coming out of our lungs and making vibration to this vocal folds. Thereafter it goes to this whole vocal tract, this part, the complete vocal tract. Now these can be represented as, for example, HT. Now this shape of HT is basically responsible for making different kinds of sound. So now sometimes it is also in case of digital signal processing, it is represented in some linear time invariant system. It is kind of a filter, and it gives shape to different sounds, and this got convolved xt with st, then we get the yt, the speech. So I can represent it something like that schematically. This is the ht, and there we get the yt. and this is our speech. This is the uh, this is the shape of the vocal tone, and this is the glottal impulse. Now, in terms of, this I have represented in time domain. So let us go to the frequency domain. So I can represent it in, say for example, uh, this is a frequency omega, and say this is the so omega. This is the power or intensity. So we have different frequencies. You can see different frequencies. Now, say the glottal shape, the based on the vocal tract, shape of the vocal tract. So it is kind of a filter. So say this is something like this. And so let me just take different, say okay, H W, and this is the symbol should be H of W, and this represent the this the variation of frequency, and once multiply these two, so we get this speech. So it is something like, say for example, like this. Now there comes the next thing, that how we do the transformation from time domain to frequency domain, and why it is required. Now if you go through the basics of any sound, then you will understand that in time domain x of t, say for example, we have a pure sine wave. It looks like something like this. Now if I want to represent, or I want to convert into say for example, in frequency domain, this j omega. So how we can do that? So let us go to the basics of polar coordinate. Now say for example, we have a real axis and imaginary axis, and we have a point somewhere here, and it makes a circle, it revolves, making radius r. Now we have, so making theta with the real axis. Now let me represent this coordinate with x and y. So this part is definitely going to be your x, this is your y, this hypotenuse of this triangle is r. Now as you know, sin theta is your p by h, and cos theta is your b by h. So you can represent x in terms of r cos theta and y in terms of r sin theta. Now from Euler's formula we know that e to the power j of theta can be represented in terms of cos theta plus I. So represent, say in terms, instead of I am writing j sin of theta, and this, if you write r over here, it will be like this as we have written. So say the magnitude of r is 1. So in that case you can simply write e to the power j of theta, then only cos theta plus sin theta of the j. Now the question is, if you have a pure sine wave, so in terms of theta I am just representing angular frequency a of omega cos of omega plus j of sine omega. Now if you have a pure sine wave of some frequency, say f, say the frequency is f, okay. Now when given the signal x of t, I want to know what frequencies with, I mean what are the major frequencies with which the signal is consist of, and it is given any frequency, it is difficult to understand because I do not know exactly, f will not be given to you. So for that purpose we take this help of this Euler's formula. So what we do, so we take different f values from w in w. So w is equal to nothing but 2 pi f, isn't it? So say for example I am taking the values of f, different values of f, say for range f1 to say f of n. Okay, so different cos omega and j, I have ij sin omega we'll get, isn't it? So we'll get, say in initially cos of say 2 pi f1 t plus j of sine 2 pi f1 t, then f2 of t, then so on, different f values. Based on that you will get different signals. Some say something like that, where if the frequency is high then there will be more number of the time period will be less, isn't it? Time period will be less, more cycle will be there, more the higher the frequency, something like that. Now what will you do? We will multiply each with this signal, okay, each with this signal, and see the signal for which f, this frequency, say for example this is f of say k, the frequency for which, say for example f of k, if f of k is very similar to that of f, the original frequency of the signal, then in that case what will you get? You will get the highest amplitude, or say the impulse, okay, I mean the intensity, sorry, not impulse, the intensity, isn't it? So if you represent all the f over here, f1 to f of n, then we'll get that in fk we got the highest intensity, and it will be j of frequency domain, and this indicates that the frequency, presence of the frequency of f, that f is nothing but the fk, isn't it? So we get the information. So for that purpose we used the Fourier transformation. Now Fourier transformation just gives you the presence of frequency, how the frequencies are, different frequencies are distributed in their presence in terms of intensity. Now this is not enough, okay, so given the frequency, we just do not want to know that what are the frequency with which any speech is consist, or rather we just also want to know that how the frequencies are distributed over the time, okay, how the frequencies has been changed over the time, say for example f and t. In time domain we get this xt, in frequency domain you get x, j, omega, and this omega. So let us just write the just omega only, so I can also write f, okay. So then we get okay, so this is the frequency domain after say Fourier transformation, FFT, say first Fourier transformation. This is the time domain, and we want to know this, how the frequencies are changing over the time. For that purpose we must have to do something. So let us again try to understand what happens in after frequency domain transformation. So we can think of a signal, any signal. When we talk about, I mean when we communicate with anyone, the sounds with which speech is, human speech is constituted, there are multiple frequencies. It is not a pure sine wave or pure cos wave. So it is basically composed of different sine waves of different frequencies. Now if you think you can visualize it something like that. So you have the frequency, say it is f, then you have another frequency, say for example f1, say it is bit frequencies with I, and so on. We have say another frequency, let me take another color. Okay, so say for example we have only these three frequencies. This is f1, okay, the middle one is say f2, and say this is the f3. So when you talk, say you will get this kind of different other frequency f of n. Now say this axis is your time and this is your x of t. So this represent the in time domain, the signal in time domain. So when we view it from this direction, we get that each of the frequencies, signal consists of different frequencies superimposed over one another, and we get something like this. So from that viewpoint, it is very difficult to understand what is the basic frequency with which the signal is consistent. So what we do is we also try to visualize from this direction. This is called nothing but the Fourier transformation. Now Fourier transformation gives you a better visualization, and this axis is then this z axis is say omega, this frequency, okay, this axis, and you get f1, f2, and say f3, and then it will be intensity of the sound. Okay, so it is a kind of amplitude versus frequency. So you get the f1, f2, and f3. Now, as I was talking about, that you get what are the frequency, major frequency with which the signal is consistent, and then you get the in a time domain you get that how the amplitudes are varying over the time. But I want to know about how the frequencies is varying over the time, and also their the powers, okay, the intensities. So the better kind of visualization is this top view. Now this top view gives you a better understanding. Say for in top view, what will you see that say for example you will get in this direction the frequencies. Okay, so I'm representing with f for better understanding, and you get here in this direction the time. Okay, and also you see we'll get some plots like that. Okay, now here you get the idea about how the frequencies are distributed over the time, and there is a way of representing it for visual understanding of how which of the frequencies have presence of the frequencies over the time and their intensity, the loudness, and all together. Okay, and this kind of representation you can get in spectrogram. Okay, so this is a better representation of the speech, because we are not going to get only about how the time and frequencies are varying over the time, but we also get an idea about the presence of the frequency as well as the loudness, the amplitude. Okay, so I'll just show you over here how this looks like and how the formats helps you in understanding the phonemes that is uttered by while communicating with anyone. So this is the basics of human speech processing system that I have already said, and this is the acoustics sound. Okay, any speech is nothing but acoustic sound. So in digital speech processing, we use some device, any recording device, to record this acoustic wave, and there comes the mechanism to record any analog or acoustic wave into some digital wave. There exists sampling and quantization. So I'll talk about the sampling and quantization later on. So this sampling and quantization helps you in getting the acoustic wave into some digital representation. Okay, so this is the digital representation of the speech, that is xt, t versus xt, that I have already mentioned in the earlier slide. Then we get the using some fast Fourier transformation, short term Fourier transformation. There are multiple types of Fourier transformation. We get the frequency versus how the frequency presence of the different frequency in the signal, in the speech signal. Now, as I was talking about, so from this viewpoint we can get about, I mean, what are the frequencies are present, and the top view we can get the idea about the how the frequencies has been changed over the time, as well as their amplitude, okay, the intensities. Now this is the called the spectrogram. So as you can see here, some red mark, continuous mark, you can visualize that is changing. I mean, there are different frequencies from lower to higher. So the lower to higher, there are different frequency and different red marks you can see. Now this part is called formant. So the lower continue line is called, say, for first frequency. So F1 frequency is F1, then you get the F2 frequency. Sorry, not frequency, formants. Okay, so there are multiple formants you are getting, and it gives you an idea about how the frequency is changing over the time, and it gives also an idea about what are the content of the speech. Okay, and there is something called fundamental frequency. Now fundamental frequency, the frequencies whose presence is highest, or the most primary frequencies, okay, that is changing over the time. This is fundamental F0 frequency, fundamental frequency. Now how we represent the phonetic sounds using these formats? Okay, so as you have already seen over here, we have different formats, say F1, F2, F3. Okay, this is the F1 format, this is the F2 format, this is the F3 formats. Okay, something like that. So it has been observed that the two important formats, F1 and F2, is sufficient enough to represent the basic sound produced by humans. There is, say, vowel and consonant. There are other sounds also. So mainly I am talking about the, say, any vowel or consonant sound that is produced by the any human can be represented with this two. I mean, it's sufficient enough to represent with the F1 and F2 formats. Okay. Now, say for example, you have uttered a sound, say for example A, and say for example C. Now what will happen? Based on the value of this F1 and F2, you can plot it somewhere. It's just like a two-dimensional coordinate geometry. Now based on these values of F1 and F2, once we plot it in the two-dimensional axis, two-dimensional coordinate geometry, then we can get an idea about which phoneme it could be, which basic sound has been uttered by the person. And based on that, there is something called IPA, International Phonetic Alphabet, and that the whole representation of different phonetic sounds that is uttered by humans can be represented in a for visualization. Okay, so I will just show you how the IPA, the International Phonetic Sound, looks like. Okay, sorry, phonetic alphabets. So how it looks like, so let me just go into it. So you can see that based on the type or manner of articulation or place of articulation where the articulation takes place, based on that, different types of sound is categorized. Okay, so nasal, trill, fricative, in this row wise you can see. So let me just make it quite bigger for better understanding. So as you can see, okay, probably the quality is not good. Sorry for. Anyways, so I was just trying to make you understand that how the different. I mean, based on the, I mean, type of articulation and place or manner of articulation or place of articulation, the whole categorization of the different phonemes has been done, and these are the different IPAs or International Phonetic Alphabets, and this can be represented. So using this diagram also, it is a very popular diagram to represent how the, I mean, exact part of the articulation and manner of articulation. Okay, and these symbols that you can see over here, you can get it from the IPA chart. Okay, International Phonetic Alphabet chart. So this is the basic representation of or understanding of the speech, human speech production system. Then comes the recognition part. How speech is being recorded or recognized by different systems, different digital systems. Mainly, as my slide is basically based on the deep generative model, or say for example deep learning. So how deep learning algorithm helps in understanding the content of the speech. Okay, so I'm just giving you a basic idea about. So for example, the person when the person has uttered a speech, say for example ABC. I mean, this is just phonetic sound, not a speech. Say ABC. So this, the initial part is A, this second part is B, and third part is C. Now, if I want to recognize and I want to convert, so initial part was the generation. Once the generation is done, I want to convert the acoustic, I mean wave file .wab, the digital representation of the acoustic signal, into text. Okay, the speech recognition part. Speech recognition. Now in that case, I must have trained my system. Okay, we must have trained this system to I mean, which part of the formats, I mean, in which part, specific time, what are the pattern of the phonemes. Okay, and what is the specific graphic, say for A, B, and C, like this. So once this training is done, then the system, the speech recognition system, can understand based on the format, pattern of the formats, what is the content of the speech. That's the grapheme. Okay, phoneme to grapheme. So based on that, once the model is get trained, we can use it for the recognition part. Okay. However, here I have shown this is the synthesis part. That means once the model learns, starts recognizing based on the formats what are the textual, I mean the content of the speech, then we can also do the reverse of that. That is, given some text, I can also make some system understandable what I mean, to generate the corresponding mail spectrogram that has been generated over here. So if we can do that, that is called synthesis part, and this specific type of synthesis is called text to speech synthesis. That means given any textual content, it can synthesize the corresponding with mail spectrogram, and there you can use different vocoders, the voice coders. There are some statistical neural vocoders, neural network based vocoders that can synthesize the given text to mail spectrogram to corresponding sound or wave file, and then we can hear the sounds, okay, or listen to the sounds, okay, and you can also make different kinds of sound given different texts. So this is the whole speech synthesis system. There comes the speech recognition also, and the representation of speech. Okay. So in the later part, I will discuss about how speech recognition is used in deep learning and how the speech synthesis is also done. So there are some mathematical representation also. I have just skipped it. I would like to include all the representation, different representation, mail spectrum. There are MFCC. There are male frequency substitute coefficient. Then male substitute coefficient. So there are different types of speech representations. So I will include all the mathematical formulation in my upcoming video, and this was just a glimpse of the basic idea of how the speech recognition and synthesis system is done, how the generation of the speech production system of human, what are the steps are there and all.